All right, we need to talk about these optimization problems. And the reason these are what we're talking about now is because when we're talking about optimization, usually what that entails is I want to find a maximum or a minimum. In certain contexts, I'll be finding a maximum or a minimum. Well, why does that come up now? Because that's what we've been finding here lately, hasn't it? Past couple of times we've been talking here together. We've been finding maximums and minimums. And we know where to look for equations. We need to look where to look for those maximums and minimums. And so on these optimization problems, that'll probably also be the case where we look. All right, so let's just start here. Looking at a few of these. Number one, what is the maximum area for a rectangle with perimeter of 400 feet? Maximum area for a rectangle with a perimeter of 400 feet. Well, hopefully, obviously, there you're thinking we need some formulas here just to get us going. So what I want to do is maximize the area of a rectangle. So guess what? I'm going to need here is the formula of an area of a rectangle. What is the area of a rectangle formula? Area of a rectangle is length times width. Okay. Now, we also notice there that the perimeter, too, is involved. And we know that the perimeter, or one such formula for a perimeter of a rectangle is 2L plus 2W. But the one main thing here, what we want to maximize here, of course, is the area one. Now, how have we been finding, from equations anyway, how have we been finding these maximums? In this case, we're finding a maximum. How do we find the maximum from an equation? Huh? We use the derivative to find what? Where does the maximum usually occur if we have a maximum of a function? At a critical number, yeah. At a critical number, and so I need to take the derivative of my function here, and then we'll go from there. Now, one thing we can see here is I do have, on this one, I have area equals length times width, which of course is in two variables, and if we can get it to one variable, that would be much to our advantage, and that's where the perimeter, usually a second equation, comes in. If you've got two variables, usually you can eliminate one of the variables using that second equation. Here's what I know. I know that the perimeter is 400 feet, and so I'm going to, of course, substitute the 400 in for the perimeter, the known value for the perimeter. And what I can do is, either way, I guess, but can I solve my perimeter equation here? Can I solve it for my length or my width? Get L in terms of W or W in terms of L. In this case, it really won't matter. All right, so let's solve this one for L. So I'm going to subtract 2W here. Then divide by 2. And so L is going to be 200 minus W, isn't it? 400 divided by 2 and 2W divided by 2. So L is 200 minus W. And so that'll help me back in here then. If I take that 200 minus W and I plug it in for L, back in the other one I'll have A equals 200 minus W times W instead of L times W. Okay? Or, put another way, I've got A equals 200 W minus W squared. All right. And so what are we looking for? We're looking for the maximum of this area. And generally speaking, when we're finding maximums, or in the case of those that have minimums, the maximum or minimum occurs at a critical number. So a max or a min usually occurs at the critical numbers. How do I find the critical numbers? Well, the critical numbers are where the derivative either equals 0 or where the derivative does not exist. So I've got to get the derivative here. And so that's why we did it in one variable. The derivative here would just be of A. The derivative of A would be 200 minus 2W. And so I want to find the critical number, so I set that equal to 0. There won't be a does not exist critical number here. And so that gives me then what? Add 2W and divide by 2 tells me W equals 100. And so that's where the maximum area occurs. That's, of course, the width that leads me to the maximum area. The maximum area then is going to be that width. And what would the length be of the, if the width's 100, what would the length be? Well, since the length is 200 minus W, right? Be 200 minus 100, which is 100 also. You may have already known that that would be where the maximum occurs. So, yeah, the length is also 100. So the maximum area is 100 times 100, which is 10,000? 10,000. Feet squared. Yeah, it is a square. A square, if you've got a full rectangle, a square is the maximum you can get out of a rectangle. Yes. Well, a square is just a special rectangle. All a rectangle means is it's 4 90-degree angles. That's what a rectangle is. And so a square is just a special rectangle. And it turns out that the square maximizes a rectangular's area. That's as good as you can get for a rectangular area with all 4 sides. Now, we'll see some here in a second where if we leave off a side or something like that, things change, which is the next one. But yes, good observation there. We do have a square. A square is the maximum area you can get out of a rectangle. Okay. All right, any other questions on number 1? Suppose a fence then is to be constructed along a river and will enclose a rectangular area. However, no fencing is going to be put alongside the river. If 200 feet of fencing is used, what is the maximum area that can be enclosed? All right, so here's my drawing. So I've got a river here, and I'm going to put a fence, rectangular shape. But the deal is I've only got three sides of fencing, nothing along the river. All right, well, what that sets up, of course, since we don't know the length of the sides that we're going to use, let's just call one of them X, one of them Y. I'll just call the one here, the shorter one I drew up here, X, and the longer one, Y. I don't know if that's going to be the case, but we'll see. All right? So we want to make the maximum area we can, but we've got 500 feet of fencing. Or 200 feet of fencing. I say 500. I meant 200. 200 feet of fencing. We want to know the maximum area we can get out of that. All right, well, again, what do we want to maximize? We want to maximize area. Right? So again, I want an area formula here to maximize. What is the area of this space here? It's still rectangle, so it's still length times width. X times y. And I want to maximize that, so I want to find the critical numbers, which means I want to find the derivative. But what's the problem here again? Two variables. So I want to get rid of one of the variables if I can, the x or the y. And the way I do that is I use the other formula here that I have. I've got the fencing, which in this case, the formula for the fencing, it is a rectangle, but there's only 3 sides of fencing. So what's the fencing? The fencing would be x plus y plus x, or 2x plus y, wouldn't it? Because I've got 2 x's and I've got 1 y for my fence. The side with the river doesn't have any fencing. So the fencing would just be 2 x's plus 1 y. All right, well, I'm looking at that, and of course I know that the fencing I have is 200. So I've got 200 equals 2x plus y. Right? And so, looks like to me, solving for y there would be easier. Solve this one for y, and then substitute that for the y in the other equation. Subtract 2x. This one turns out pretty easy. So I just substitute that in for y in the area equation. With me? Is that okay? So the area is x times 200 minus 2x, substituting the 200 minus 2x for y. Go ahead and multiply that out. So that's a equals 200x minus 2x squared. That's what I want to maximize in terms of one variable. Well, where does the maximum occur? Usually at the critical number, which has to do with the derivative. So let's do our derivative here. That would be, what, 200 minus 4x. And in this case, the critical number would be where it equals 0. So I set that equal to 0. Let's see. Easiest way, we add 4x, divide by 5, times 4. 50 equals x. And so the maximum area is going to be when x is 50. What's the y value? Well, the y from previous, we know y is 200 minus x, so y would be 200 minus 2 times 50. I now know the x is 50, so this one's not going to be a square, is it? It's 200 minus 100, which is 100. So the y value is 100 when the x, so the maximum area is 50 times 100. 5,000. Again, this is feet, right? Feet square. Sound okay? So that's the maximum area we get out of our 200 feet of fencing. Question or concern? All right, number 3. Number 3, we've got another rectangular area. In this case, we know the rectangular area to be 2,500 feet squared. It's going to be divided into 2 pins where the middle fence is parallel to one of the sides of fencing. So I've got a rectangular area fenced all the way around here. I'm going to divide it into 2 by putting a fence. It doesn't matter which way you go with it, but let's just go this way. So I put a fence down the middle to make it 2 pins. Find the dimensions of the rectangle that would minimize the cost of the fencing. So we're going the other way here. And we'll talk about that in just a second. But we also know the maximum occurs at critical numbers, so do minimums occur at critical numbers. So we can do it both ways here. The minimum, so we want to minimize the fencing. So I need a fencing equation, once again. Well, the easy way to do the fencing equation is, again, we've got one side is x, and let's don't divvy it up here. Let's just say y is, there's no real need to specify because it could be down the middle, it could be to one side or the other. It doesn't really matter in our case here for our purposes. So let's just call the whole distance across the bottom there y. So fencing-wise, what have I got? Well, how many x's do I have? 1, 2, 3 x's. And I've got 2 y's. Three x's plus 2 y's. That's what I want to minimize, which means find the derivative, set it equal to 0 usually. Or it does not exist. Some cases that'll come up. All right. But, again, before I do the derivative, I need the fencing equation in terms of one variable, so I need another equation maybe to help me along the way. Well, in this case, the other equation is the area. What's the area of this thing? Well, again, just look at the total area. Don't divvy it up here and say this is half, this is half. It's just the total area is a rectangle, isn't it? X times y, again. Which I know the area here is 2,500, so I've got 2,500 is x times y. Which there's a lot of ways you could get x times y to equal 2,500, but what do we want to do with that? What is the purpose of that equation? Well, the purpose of that equation is to get one variable in terms of the other. So let's solve this one for y. Plug it in for the y in the other. You can go the other way if you want, but to solve this one for y, wouldn't I just divide by x? So 2,500 divided by x is y, and so I'm going to drop that one right in here in place of the y. So I have the fencing is 3x plus 2 times 2,500 over x. So far, so good. Well, that's f equals, let's go ahead and clean that up a little bit. F equals 3x plus 5,000 over x. Or, for purposes of what I want to do with that, I want to take the derivative of that. I'm going to say this is, move over here a little bit, f equals 3x plus 5,000 x to the minus 1. Wouldn't that be the best way to go to get the derivative? Change 5,000 over x to 5,000 x to the minus 1. Okay? So we want to minimize that. Where does the minimum occur? Usually at critical number, which is tied in with the derivative. All right, so let's see. Derivative equals 3 plus, well, actually bring down the minus 1, times 5,000, subtract 1 from the power, so it's 3. The derivative is 3 minus, let's just write it this way, 5,000 over x squared. One other note, of course, too, on this 5,000 over x, if you didn't change it to the x to the minus 1, you could use a quotient rule on the 5,000 over x if you so choose, but you should get, this is what you should get, 3 minus 5,000 over x squared. All right. So what do we want? We want the critical numbers. Now, on this one, we do have the other type of critical number come into play, because critical numbers are where the derivative equals 0, or what else? Derivative does not exist. Well, where does this derivative not exist? Well, it would be where x is 0. But in the context of this problem, would it make sense to have x equal 0? Why not? If we had x equals 0, we have no fence, okay? Yeah, it'd just be a straight line. It wouldn't hold much of anything. Maybe snake, but all right, not even a snake. Yeah, it'd just be just be out there. It'd just be a long strip. I don't know what. Wouldn't hold anything. The goal is to hold something. Okay. So x equals 0 is out. So we just want to set that equal to 0. So 0 equals 3 minus 5,000 over x squared. How do we solve that? A couple ways. I think the way we've been going with that is multiply by x squared. Multiply everything by x squared. Both sides. X squared times 0 is 0. So x squared times 3 would be 3x squared. And then the x squared times the 5,000 over x squared would just be minus 5,000, wouldn't it? So that looks like a nice enough equation. What do you want to do? Add the 5,000 divided by 3. So we get x squared equals 5,000 over 3, which means x is plus or minus the square root of 5,000 over 3. But again, x being a side length, what about negative square root of 5,000? I don't think so. So x is definitely the square root of 5,000 over 3. Or however you want to put that. Could clean that up a little bit. But now this one does, it actually does ask for the dimensions, the rectangle that would minimize the cost. So x is one of the dimensions. What else do I need? Y? So the y, go back to this one, y is 2,500 divided by x, so it would be 2,500 divided by x, which is the square root of 5,000 over 3. Now, and you can get decimal forms of those. But let me show you one thing real quick here. If I clean this up a little bit, let's multiply the, so that's one form of the answer. And like I said, decimal approximation, what are they? What is the decimal? 40.82 and then 61.24. Okay? Well, the other thing I was going to show you was an interesting little connection here. If I multiply, take the y here, and multiply by the square root of 5,000 over 3, top and bottom. And of course that, I'm running low space here. I didn't budget my space here. Let me go over here just a bit. Yeah, that's what I was thinking about doing here. If I can find my eraser. Okay. Okay. So I've got 2,500. So the top, y is going to be 2,500 times the square root of 5,000 over 3. And I'm just going to leave that as is. The bottom would be square root of 5,000 over 3 times square root of 5,000 over 3 would be 5,000 over 3, wouldn't it? Now let me focus on this right here. 2,500 divided by 5,000 over 3 is what that is, right? Well, that's 2,500 times 3 over 5,000, right? which the 2,500 will cancel into 5,000, leave me 2 on the bottom. With me? So that'll be, so all this is 3 over 2 times the square root of 5,000 over 3. Which, what's the square root of 5,000 over 3? That's x. So it's 3/2 of x. So it's 1.5 times the size of x is the y value. So there's usually a connection like that. There's different things you say about that. But anyway. All right. And then, of course, you can, I guess, if you want to get real technical about it, if I wanted to simplify, let's see, that's got at least 100. I could pull out 100 on that. So it'd be 10 times 50 or 500. No. 10 times 50. Oh, and then, actually I could pull out, what could I pull out there? 2,500. I could pull out 2,500. So, yes, sir. Okay, yeah. Thanks for mentioning that, because I did want to mention that. How do we know it's a minimum? How do we know it's a maximum? Well, that gets back to, we didn't really get into it, but there is a difference between it. And how do we know if it's a minimum or a maximum? Well, we look on either side here. If I look on either side of my, for my function here, my derivative here, if I plug in an x value, well, it has to be something bigger than 0. Something between 0 and 40.8, so 1. I'd look at 1 here. Plug in x to be 1, right? So I guess I'll have to move this again. We're not going through this whole deal, but technically speaking, yeah, we should be seeing if this is a maximum or a minimum here. And so I've got x is 0, and then out here about 40.8 is my critical number here. And so if I look at x as 1, f prime of 1 is 3 plus 5,000, so that's positive 5,003. So I've got an increasing graph there. And then on this side, say f prime of 41, what have I got there? Well, 3 times 41 would be 3 times 41 plus 5,000 divided by 41. Oh, no, I'm sorry. I'm plugging in the wrong place. It might be right, but I need to plug it in right here. 3 minus 5,000 over x squared. Let's try that again. Oh, well, I was right. Okay, so 3, it'd be 3 minus 5,000. No, I wasn't right. 3 minus 5,000 would be a negative 4,997. It's negative. Yeah, this is going to work out better here, because then on 41, I'd have 3 minus 5,000 over 41 squared. Which is point. It's not very much, but it is a positive. .02, positive. So it's increasing there. So I've got a decreasing to an increasing. What have I got at 40.8? I do have a minimum. Okay, and so that's just the way it usually works out. If we did the same thing on